Thank you for that introduction. Like Tom said, my name's Iryna. I'm from the University of Washington, where I work with Tom Quinn and Jessica Work, and I'm going to talk about a project that I started as a Blue Waters graduate fellow that is currently pending submission in AppJ. So, thanks to recent observations through quasar absorption lines, we now know that the CGM has the majority of baryons, or galactic baryons, including the majority of metals. And these baryons have a complex multi-phase structure that's shaped by metal-rich outflows from the galactic disk and pristine inflows from the IGM. And in recent years, simulations have really struggled to reproduce this structure. Specifically, simulations using purely thermal supernova feedback that was calibrated to reproduce galactic disk structure struggled to reproduce the observed column densities of low, intermediate, and high ions. So here are just a couple of examples from recent works. And so there have been lots of different solutions proposed, some of which we heard today, AGN feedback, increased resolution, radiation pressure. But I'm hopefully going to convince you that cosmic rays should be part of that solution. So cosmic rays are charged particles, mostly protons, that are accelerated to relativistic velocities in extreme shocks like supernovae. And so we observe cosmic ray pressure in the disk to be roughly in equipartition strength with the magnetic and turbulent energies, and we observe supernovae to be progenitors of cosmic rays. So even if you're not concerned with reproducing CGM structure and using cosmic ray feedback as motivation for that, you should still consider cosmic ray feedback just to make your stellar prescriptions more robust. And cosmic ray feedback has been around for at least a few years now. And in fact, early simulations showed that when you include cosmic ray feedback in galaxy simulations, you do drive stronger outflows. And those outflows, the cosmic ray pressure provides non-thermal pressure support to gas, which could explain some of the low density gas that we observe. And so Munir Salem was one of the first people to take cosmic ray driven outflows and look at what happens to the CGM. And the results were really exciting. So compared to a control galaxy or a controlled model without any cosmic rays, see that models with cosmic ray feedback much better reproduce the observed column densities of carbon-3 and oxygen-6, which trace the cool and warm gas of the CGM. And these column densities are some of the best matches that have been around in the last few years. And this is really exciting, but there's a catch, and is that cosmic ray feedback is really poorly constrained. So we don't have a consensus as to what fraction of cosmic ray or of supernova energy should go into cosmic ray feedback. We don't have a consensus as to how quickly we should model cosmic ray transport moving, so that's either the diffusion coefficient or a streaming velocity. But most importantly, there's no consensus as to what cosmic ray transport approximation we should use in simulations. And the two main branches break down to diffusion and streaming. And I'm going to spend the next 8-ish minutes talking about how the choice of cosmic ray transport actually really matters, and we need to be careful when we model simulations or model cosmic rays in simulations. So when I say modeling cosmic rays, I don't mean individual protons moving around magnetic field lines. Like everything else in galaxy simulations, we model cosmic rays as a fluid, and this fluid moves both with the thermal gas through advection, and it moves relative to the thermal gas through either diffusion or streaming. And both diffusion and streaming are approximations to bulk scattering of the cosmic rays through small variations in the magnetic field lines. And the distinction comes from the source of the variation in the magnetic field line. So if the magnetic field or the variation in the magnetic field line is caused by external gas turbulence, then the cosmic rays are said to be diffusing. And if that variation is caused by the cosmic ray streaming instability, then the cosmic rays are streaming. And so to test this difference I built on the work of Munoz-Salem, and I added anisotropic cosmic ray physics into ENSO, and I ran a simulation suite of isolated disk galaxies, starting from modified Agora initial conditions. And so some of these galaxies are pictured here. And except for the control galaxy without any cosmic rays, these all have 10% of their supernova energy injected as cosmic rays. And the only difference between them is the choice of cosmic ray transport. And for the sake of time, I'm just going to talk about these two galaxies, so the anisotropic diffusion and anisotropic streaming case, just to highlight the difference between the two extremes of cosmic ray transport. So this is a movie of the temperature evolution of the two models. The top row shows the density-weighted projection of the temperature, and the bottom row is the slice. And so what jumps out visually is that in the diffusion model, you see a large reservoir of cool gas that extends to very large radii. But in the streaming model, you see a much more multi-phase CGM, so you have cool gas clumps right alongside of hot gas that's outflowing. And so this temperature difference will have some interesting effects on the ionization structure. So I wanted to start by comparing the column densities to observations. So this is the neutral hydrogen, carbon-3, and oxygen-6 column densities, the scatter, or as a function of impact parameter from the center of the galaxy. The scatter points are Cos halos, or data from Cos halos, and the pixels are colored by the probability of the column density at that radius. And so the model without cosmic rays had purely thermal supernova feedback in this Milky Way mass halo. It did not drive any outflows. But both models with cosmic ray physics did drive strong outflows. But just by looking at the distribution of column densities, it's really hard to discern which model might be a better fit. Both have much stronger column densities than the no cosmic rays case, although they still underpredicts the data because this is an isolated disk setup that wasn't tuned to reproduce realistic CGM metallicities. So looking at oxygen-6, just as an example, we see that looking at the projected oxygen-6 column density, in both the diffusion and streaming model, the maximum column density strengths are pretty similar. They both reach roughly a few times 10 to the 14. But the distribution of that oxygen-6 column density is pretty different. So like the temperature, in the diffusion model, you have a strong column densities of oxygen-6, kind of relatively uniform in strength, centered around the galaxy center. But in the streaming case, you have a more patchy multi-phase distribution. And if you look a little further at the phase diagram of temperature and density colored by the oxygen-6 mass, so the dark pixels are where you expect most of the oxygen-6 to lie. In the diffusion model, that oxygen-6 is predominantly photoionized, whereas in the streaming model, there's a large fraction of the oxygen-6 is also collisionally ionized, which is much more likely to be a realistic scenario. And so the difference between the two models boils down to the difference in the distribution of cosmic ray pressure in the CGM, which is what's driving this ionization structure. So in the anisotropic diffusion case, if you look at the ratio of cosmic ray pressure to gas pressure as a function of radius, you see that, or colored by the gas density, you see that cosmic ray pressure dominates near the galactic disk at high gas densities, whereas in the streaming model, cosmic ray pressure dominates at larger radii and at low gas densities. And this difference is a fundamental difference between the two transport models, and it's not something that can be easily reconciled just by tuning runtime parameters of one model or the other. And so this really calls for the need to self-consistently model cosmic ray transport between both diffusion and streaming, because realistically, both are happening in the galaxy. And so, in summary, Cosmicray physics, I think, is a really exciting step forward in simulations, and we should really think about including them in simulations, not just of the CGM, but galaxies in general. But before we can trust the predictions that these simulations make, we really need to improve our Cosmicray feedback and transport. So, thank you.
So we've got plenty of time for questions. So Ben.
Yeah, so there's MHD, and both of the models I talked about had full anisotropic treatment.
Go ahead.
Visually, it seems like the topology is a little different in the way the gas temperature and density flows out. Would that be something that could be observed and perhaps be telling as to which one might be dominating from the observations? And maybe the observers can tell me whether people have explored this relative to the plane of the disk.
Yeah, I mean, I hope so, and certainly at least the temperature structure and velocity structure of the disk is something that can be probed by observations. Yeah, that's all I got.
Do you see any difference between the disk structure when you do the streaming and diffusion? Is the disk stay the same or different?
Sorry, I thought. Yeah, so the disk structure does vary between the models, but I don't have hadronic losses implemented yet, so I suspect that that difference will be at least modified once that's there. So basically, the more cosmic ray pressures in the disk, the puffier that disk ends up being. And in the anisotropic diffusion model, the cosmic rays tend to stick around the disk more because in the streaming model, I have cosmic ray losses due to alpha and wave heating.
All right, quick question.
Oh, it's basically the same. Yeah.
Quick answer. Let's thank Iryna once more.